Okay. Bismillahirrahmanirrahim. Welcome to the class of Irrigation Engineering for 4th of May 2021. This is section B and C. Already 18 students are with me. So we were studying the topic of canal outlets in the last week. In 1 hour lecture, we have started the topic of outlets. And prior to that, we have gone through the topic of water, crop water requirements and crop soil water relationship. So before the other student join, because only 18-20 students are with me, if you have some questions, 26 students are with me. If you have any question in the last lectures, you are welcome. किसी का कोई सवाल है, कोई suggestions है, तो this is the time to ask the questions. ज़मीर क्या हाल है आपके? Are you available, Zamir? If you people getting my voice, आपको आवाज आ रही है?
जी सर, आवाज आ रही है।
अच्छा, तो ज़मीर बोल क्यों नहीं रहा? Gone out. Log out हो गया। जी ज़मीर, आवाज क्यों नहीं आ रही है आपकी? अनम्यूट करो अपने आप। क्या हाल है, सोए हुए हो? आवाज नहीं आ रही है आपकी। नहीं, हैंड रेज हुआ है, नो वॉइस। Okay. Who will tell me? There are 3 kinds of outlets depending upon their discharge dependence on water levels upstream and the downstream. There are 3 kinds of the outlets. Who will tell me the names of these 3 kinds of outlets? Please raise your hand. Zamir, अपना हाथ नीचे कर दो. Okay, 120 will like to tell the 3 basic types of outlets.
मॉड्यूलर और सेमी मॉड्यूलर सर।
Modular, non-modular or semi-modular. What is the other name for modular and non-modular? Yeah, modular का other name क्या है? Modular का एक और नाम भी है।
सर
Rigid outlets. ठीक हो गया? So 134 have responded. Okay, who will tell me what is a semi-modular outlet? Raise your hand. So can I ask Bilal Afzal if he is available? Bilal Afzal. Bilal Afzal, are you available? Bilal is not responding. मेरी क्लास हो रही. Bilal Afzal, you are not responding. Okay, let us remove him. If you're available, please write in the chat box or raise your hand. Yes, he is available. So why not you responding? So write in the chat box. Ji Bilal, can you tell me what is a semi-modular outlet? Maybe you can write in the chat box if your mic is not working. No. Not ready to reply. Ji Bilal. Okay. So Zamir, if your mic is working, please reply what is a semi-modular outlet? हैंड रेस कर दिया जमीर तुमने, लेकिन जवाब नहीं दे रहे. ओके, रोल फहद अफजल.
Yes, sir.
Can you tell me what is semi-modular outlet?
So semi-modular outlet is an outlet in which the discharge only depend on the water level in the distributory.
Discharge of
distributory canal.
किस चीज का डिस्चार्ज डिस्ट्रीब्यूटरी पे डिपेंड कर रहा है? In which
water level, sir.
दोबारा बोलो.
सर जो डिस्ट्रीब्यूटरी कैनाल के अंदर जो वाटर लेवल है उसका जो डिस्चार्ज जो जाएगा सेमी मॉडुलर आउटलेट है, तो वो डिपेंड करता है सिर्फ डिस्ट्रीब्यूटरी कैनाल के डिस्चार्ज के ऊपर, हेड में. वाटर कोर्स के हेड के ऊपर डिपेंड नहीं करता.
ओके, अब इकट्ठा मिला के पूरा दोबारा बताओ.
सर द डिस्चार्ज ओनली डिपेंड्स ऑन द वाटर लेवल व्हिच इज इन द डिस्ट्रीब्यूटरी कैनाल.
मैं वही पूछ रहा हूँ, डिस्चार्ज ऑफ व्हाट? क्या यही डेफिनेशन है? डिस्चार्ज डिपेंड, यही डेफिनेशन है और तुम इसको एक्सप्लेन नहीं कर रहे. कौन सा डिस्चार्ज? सोचा तुमने? नेमतुल्लाह, आपका टीवी को बंद करो या माइक को बंद करो. Okay. Fahad, you should be clear that discharge of the outlet depends upon the water level in the distributory. So if it was not mentioned over there, you should have known it. So discharge of the outlet is dependent upon. So Bilal Afzal sir, mic is not working. तो बेटे फाइनल ईयर में अब तक तो माइक सही हो जाना चाहिए था आपका. ज़मीर सेम टू यू, अपने माइक ठीक करो. Okay. Okay, we start with our today's lecture. So just for your repetition, revision, we have three kinds of outlets, basic kinds. One is the modular or rigid. Second is semi-modular. Third one is non-modular outlets. So as we have been informed that in case of semi-modular outlet, the discharge of the outlet. So please keep in mind, discharge of the outlet depends upon the water level in the canal or distributary or parent channel and is independent of the water level in the water course. And similarly, we can define the other two kinds also. There were further for each basic type of the outlet, there can be a number of different types. For example, in non-modular category, pipe or barrel can work as a non-modular. A variant of that pipe outlet is Scratchley outlet. In semi-modular, we have open flume or an orifice kind of outlet, flume kind of outlet, and orifice kind of outlets. And in rigid, we have two kinds, one with the moving part and one without moving part. In without moving part, I think we informed you, one of them is Gibbs outlet, and its working was informed to you. Pipe outlet was shown to you, Scratchley outlet was shown, its construction was shown to you. Let us see. It consists of a pipe which connects the distributary with a water course. There is a pipe which connects distributary with the water course, and in between, close to the water course on the downstream end, there is a cistern or there is a chamber. There is a cistern or there is a chamber in which water level rises to nearly same level as a full supply level in the canal, except for small head loss. So water is released to the water course with the help of a small opening on the side wall of the chamber that they call it as orifice. So through this orifice, water is released to the downstream side. It is a kind of non-modular outlet, and reason is because flow through this orifice is dependent upon both water level on the downstream side and water level on the upstream side. Okay. Then we started, I think, this semi-modular kind of outlet, and you were informed that in semi-modular outlet, discharge is only dependent on the upstream water level, the water level in the channel, and the downstream water level don't affect the flow through the outlet, don't affect the discharge through the outlet. And the principle or the mechanism which make it independent from the downstream water level is creation of the hydraulic jump or standing wave, they call it. Creation of hydraulic jump or standing wave, which is shown over here. And that can be created either by constriction, by reducing the width of the outlet at a certain place, or by producing a steep channel within the throat of the outlet, within the length of the outlet, creating a steep channel, steep slope, and over there supercritical flow will occur. And downstream of that, if it is subcritical flow, so a hydraulic jump will be created. Most simple of them is simply is Harvey outlet, in which if we see its longitudinal section, we see simply a concrete pad underneath and the side walls. And if we see it in a plan view, we see a constriction. Upstream side is on the right hand side. We see a constriction and then an expansion, like a Venturi flume. They reduce the width of the throat at the throat and then expand it. Because of this constriction, standing wave is created, and it works like a semi-modular outlet. And it was proposed by Harvey in 1912. Most of other outlets are a variant of this. So before going to other semi-modular outlet, rigid outlet was informed to you. In this kind of outlet, if water level rises in the so in this kind of outlet, in rigid outlet, let us first see its construction. What are different component of this kind of outlet? It mainly consists of a pipe. On the downstream end, this pipe makes a bend or makes a spiral shape, and it rises also, and then it enters into a chamber, and they call it Eddy's chamber. So this one is Eddy's chamber. So if we see the plan view, this pipe is bent in plan view, and it is rising also. That rising we can see in the longitudinal section, and the spiral bend we can see in the plan view. So when it enters into the Eddy's chamber, which starts from here in the plan view and ends over here, this part is Eddy's chamber. So within the Eddy's chamber, there are steel plates or baffle plates installed inside it, with their bottom at a certain at a higher level, not fixed. Bottom is not fixed at the bed of the chamber, rather bottom is raised. So if we see the plate in the longitudinal section, that plate look like this. Bottom is creating an opening underneath, and top is closed. So when normal flow is passing through this, then these plates are not hampering the flow. But when water level in the distributary rises and more flow like to enter into this chamber, then water level in this chamber rises because of the vortex flow, because of the rotational flow. The water level in the chamber tries to rise up, and these baffle plates, 1, 2, 3, 4, 5, a number of these baffle plates whose bottom level is fixed after experiments at a suitable level. So when water level in the Eddy's chamber rises, these baffle plates are these steel plates restrict that, obstruct that, and dissipate the excess energy which was available with the water. So they allow, because of this dissipation of the energy, only the fixed amount of the discharge passes through this Eddy's chamber, and then it is released on the downstream side. The effect of the downstream water level is removed. Effect of the downstream water level on the discharge is eliminated by releasing a supercritical flow through the outlet of this through the downstream side of this outlet. So upstream effect is taken away. Upstream effect is taken away with the help of the Eddy's chamber and the baffle plate inside it, and the downstream effect is taken away. A downstream effect is removed because of release at a supercritical flow on the downstream side. So that is how this kind of outlet works without effect of the upstream water level and the downstream water level, and more or less it flows at a constant discharge. When it flows at a constant discharge and there is no effect of upstream and the downstream water level, so we can call it as a rigid outlet or a modular outlet. And this kind of construction it was given by Gibbs. So that is because of his invention, so we call it as a Gibbs module or Gibbs outlet. So that is how constant discharge or a rigid outlet works. One kind of this. There are other kind of construction of rigid outlet. For example, in Ghaffur's outlet, there is another kind of outlet, Ghaffur's outlet. If somebody want to see its construction, you can see its construction in book of Iqbal Ali. A cross section is made over there, and a steel plate, which is movable steel plate, is used at the top of the pipe. There is a straight pipe, and water passes through it, but at the roof of the pipe there is a steel plate, and if the discharge is increased, a reverse discharge starts from that plate, and that tries to reduce the discharge. So that works in another fashion. So there are different kind of construction for rigid outlets. So Gibbs is one kind of this outlet, and its actual construction is shown over here. This is the Eddy's chamber we were talking in the previous, this part is shown over here in the actual construction as the Eddy's chamber. You can see the steel plates. you can see its plan view and its downstream side view. So that is how it works. Any question in this, you are welcome. इसमें किसी का कोई सवाल जवाब कोई मसले हैं तो पूछ लो.
So baffle plates का level same है throughout the chamber.
बैफल प्लेट्स का लेवल सेम ही है क्योंकि अपस्ट्रीम बैफल प्लेट अफेक्ट्स द मोस्ट, तो मेरे ख्याल में सेम ही है. और दे डिसाइडेड बेस्ड अपॉन द डिस्चार्ज रिक्वायर्ड बेस्ड अपॉन द विड्थ अवेलेबल इन द एडिस चैम्बर. एंड अ टिपिकल जिप्स मॉड्यूल विद इट्स डायमेंशंस इज गिवन इन बुक ऑफ इकबाल अली. उसमें इसके डायमेंशंस वगैरह और लेवल्स वगैरह बताए हैं. अगर इकबाल अली की बुक का 8वां चैप्टर देखोगे तो उसमें इसका डिफरेंट डायमेंशंस और रेडियस और लेवल्स बताए हुए हैं. नॉट मच पॉपुलर. इफ वी सी हाउ मेनी of them are used, we can see very less number of constant. This was in 44. JIPS module was 74 modules were used out of 40,000 outlets surveyed at that time, so very less number. We will be reading in the next after a few slides that this fixed outlet or rigid outlets or modular outlets are used in case of if we have to put an outlet in branch or main canal, which usually we don't provide. So, but if due to certain restrictions, certain compulsion, if we have to place an outlet in a big canal like branch canal and main canal, then it is better to put a fixed discharge outlet that is a kind of JIPS outlet. So that is its usability. Okay, there are some important definitions which you people should be knowing. And they are required in the design phase also. For example, one important parameter with respect to outlet is flexibility of the outlet, and another important parameter is sensitivity of the outlet, and few more definitions will be there in these slides. So first of all, what is the flexibility? Flexibility actually tells us how much the outlet discharge varies with the variation of the discharge in the distributory. That is its background. It shows the capacity of the variation of the discharge of the outlet, or the capacity or the flow in the outlet with the variation of flow in the channel, in the distributory channel, in the parent channel. So mathematically it is written as flexibility is, let us first introduce to you these symbols. Small q is representing the discharge in the water course or outlet. Small q is representing discharge in the outlet or water course, while capital Q is representing the discharge in the parent channel. Got it? So small dq over q. So d small q over small q, that is the variation of the discharge in the outlet with respect to the design discharge. Change of discharge with respect to the design discharge. Or we can say this is the rate of change of discharge in the outlet. Got it? So our unit variation of the discharge in the outlet. So similarly, this is the rate of change of discharge in the distributory, d capital Q or over capital Q. So this is the rate of change of discharge. उन्हें कोई क्लास हो रही है 12 बजे. So dq over q is the variation of the discharge in the outlet with respect to its original discharge, and this is the variation of the discharge in the distributory with respect to its design discharge. So ratio of these two variations is called as the flexibility. If rate of change of discharge in the outlet is same, dq over q, if this rate of change of discharge in the outlet is same as the rate of change of discharge in the distributory, so then f value would be equal to 1. So if that is a condition, then we say that this kind of outlet is proportional outlet. The rate of change of discharge in the outlet is same as the rate of change of discharge in case of distributors. So, and if rate of change of discharge in the outlet is less than the rate of change of discharge of the distributary, then we will be saying this as a subproportional outlet. So then F value calculated will be less than 1. And if it is more than 1, it means it is hyperproportional. So we should be knowing these values. We should be knowing this terminology. First, we should know what do flexibility represent. Flexibility represents the capacity of variation of the discharge in an outlet with respect to variation of the discharge in parent channel. So that should be made clear. And then we should know what we will be calling an outlet. If its flexibility is 1, we will be calling it as a proportional outlet. And if its flexibility is less than 1, we will be calling it as a subproportional outlet. And if it is more than 1, we will be calling it as a superproportional, hyperproportional outlet. Got it up till now? We have defined it and what does it represent, and mathematically how can we show it. Now, if we want to calculate the flexibility of an outlet, either we should have these variations, change of discharge, if we have practically outlet available with us, or we can calculate it from the discharge equations also. For example, if we have a discharge equation in the channel, like the equation of Manning's equation or like the equation of the Chazy equation, so we can write the discharge as a function of depth in the channel. Got it? The discharge equation in the channel or discharge equation in the outlet can be written as a function of depth, slope, Manning's roughness, these things. So if we think that in a certain channel slope remains constant, n remains constant, we can say that the discharge equation can be written in this form. Discharge in the main channel can be written as Q is equal to all the parameters which are constant, let us say K, and depth power an exponent n. So can we write Manning's equation in this form by only considering that the depth varies and all the remaining parameter like n, like slope, that remains constant. So depth is representing also the hydraulic radius, depth is representing also the area. So all those terms which are dependent upon depth, that will be combined over here in depth term. All remaining terms like n and slope will be collected in this one constant value, K value. So we can write the discharge equation in the parent channel or distributary channel in the form of Q is equal to coefficient times depth power and exponent n. So n is the exponent of the discharge equation for parent channel. Similarly, we can write the discharge equation for the outlet by writing the depth or head in the outlet representing with the h value. So we can write that the discharge is equal to a constant value K2. To differentiate from K1, we write it over here, K2 times head of the water which is causing the flow in the outlet, power an exponent m. This exponent depends upon shape of the outlet, whether it is orifice type outlet opening or it is a flume kind of the outlet. Similarly, this exponent n, this depends upon the shape of the distributary channel, whether it is rectangular channel, whether it is trapezoidal channel, whether it is a trapezoidal channel with a certain slope. So all these things control the n value in the discharge equation for distributary and m value for discharge equation for outlet. So just now bear with me that discharge in the parent channel can be written in this form and discharge in the outlet can be written in this form. So n is the exponent. So this n is not Manning's roughness coefficient. So don't mix it. It is simply the exponent of depth term in discharge equation. Similarly, m is the exponent of the depth terms or head terms in outlet. So if these things are known, we can prove that F flexibility is equal to from this thing dq over q divided by d capital Q over q can be replaced with m over n into d over h, or we sometimes we write it m over n divided by h over d. This factor h over d, this factor h over d is given a special name, and this is called as the setting of an outlet. And by setting of the outlet means the ratio of head in the outlet to the depth in the channel, depth in the parent channel. If I show this thing in the figure, if this is a semi-modular outlet, let us say this is a plan view, we can see the depth and head in the longitudinal section of this outlet. So this is the longitudinal section of outlet and cross section of the distributary. So over here, if distributary depth is represented with the symbol capital D, and here's the crest of the outlet or bed of the outlet. So depth of the water above the crest will be called as a head causing the flow in the outlet. So H is a head causing the flow in the outlet. So H is head in the outlet, D is the depth in the channel. So discharge in the channel, distributary channel, is a function of this depth. Capital Q is equal to a coefficient K1 times depth powers n. This n varies from 5 by 3 to neighboring values depending upon the shape of the distributary channel. Similarly, the discharge in this outlet will be function of how much is the head above this crest. If you consider this as a weir, you know the weir equation says that discharge is equal to coefficient into the width of the weir times h power 3 by 2. And if it is an orifice, if this outlet is an orifice, you know that the discharge is equal to coefficient of the orifice times flow area times 2gh under root, h under root. So over here, so discharge will be function of h power half. While in case of the weir or open flume, it will be function of 3 by 2. So in this way, this exponent varies with the type of the outlet. Similarly, the exponent of discharge in distributary varies with the shape of the distributary channel. So that is how these symbols are used. So D is the depth in the parent channel, D is the depth in the parent channel, while H is the head above the crest of the outlet. So H over D is a particular term, is given a name, setting of the outlet. If we see this setting of the outlet in this longitudinal section, when you will be designing the outlet, you will be deciding what should I keep H over D. When you decide what is the H over D, it means crest level you will be deciding. For example, I want to make an outlet with H over D is equal to 1. What does it mean? It means whatever is the depth of water in the parent channel, same should be the head in the outlet. It means you will be placing this crest at the bed level of the channel. Got it? So when you will be designing the outlet, one important factor will be this setting of the outlet. Setting of the outlet, you should know, represents H over D, is represented mathematically by H over D. H is the head above the crest of the outlet, D is the depth in the channel. Sometimes we call it G over D. G is the gauge above the outlet and D is the depth in the channel. So other symbols can be used, but you should know the parameter itself. So ratio of the head in the outlet to the depth in the parent channel, H over D, is the setting of the outlet. If you have decided that the setting should be equal to, let us say, 0.5, H over D should be equal to 0.5, it means you are saying that crest should be kept at 0.5 times of the depth in the channel. So you will be putting a crest at a higher elevation. So that is how this setting will be utilized in case of design of the outlet. And now you can ask, sir, from where we will be getting this setting of the outlet, whether it should be 1, whether it should be 0.5, whether it should be 0.9, from where we will be getting it. That we will be getting from the, again, from this information, this knowledge. Uh, Here they have given, we will come to this derivation in the next slide. There is a derivation of this m over n d over h. But if we hold that for a minute, let us see the use of this equation first. If we know that f is equal to m over n divided by h over d, or m over n multiplied by d over h, if we know flexibility is equal to this, and if we have a channel shape for which we know what is the exponent of the discharge equation, and if we have the outlet type, or if it's our flume type outlet, for which we know what is the exponent of that discharge equation. So if m over n, which are dependent upon the shape of the parent channel and shape of the outlet, if those are known to us, then we can find what should be h over d if we decide what should be the flexibility. For example, sometime we say, I need an outlet which is a proportional outlet. Means you are saying you need an outlet with flexibility equal to 1. Sometimes you say, no, I need over here an outlet which is hyperproportional. It means you are saying that flexibility should be more than 1. So you decide a value of suitable flexibility, for example, 1.1, 1.15, like this. And then knowing the exponent m over n, you can calculate the setting of the outlet required. Just for an example, if there is a trapezoidal channel with side slope equal to half to 1, its exponent of the discharge equation can be found to be equal to 5 over 3. If you write the Chazy equation, and if you write that equation for a wide rectangular channel, you can see that that equation can be written as Q is equal to some constant parameter into depth power 5 by 3. You can check it. When you write the Chazy equations, you can see that it will be equal to 5 by 3. And so if you have a trapezoidal channel, then its exponent is equal to 5 by 3. And if the flume is, if the outlet is open flume outlet like a weir, its exponent m is 3 by 2. If we put this n value m by 3 over here, m value 3, n value 5 by 3 over here, m value 3 by 2 over here, the result will be that flexibility is equal to 0.9 times d over h. So this equation is valid for our parent channel, which is trapezoidal on the upstream side, and for an open flume outlet, for an open flume, not for an orifice. So for open flume outlet, flexibility can be set to be equal to 0.9 times d over h. So if you decide that I need a flexible outlet, a proportional outlet, so put f is equal to 1. So h over d can be calculated, h over d can be calculated as equal to 0.9. So when h over d is known to you for proportional outlet, it should be 0.9. You can put in the drawing that crest should be, if depth of the water in the channel is known as 3 meter, so 0.9 times 3 meter, you can calculate that the crest should be from the water level, it should be 2.7 meter. So in this way, we decide what should be the crest elevation using the concept of setting of an outlet, using the concept of flexibility. So first we decide whether we need proportional or hyperproportional or subproportional. Based upon that, decide what should be the flexibility value. Put that flexibility value in the equation of f is equal to m over n d over h. Find the m exponent of the discharge equation in parent. M is the exponent of the discharge equation in outlet, and n is the exponent of the discharge equation in the parent channel. Put those values, and then you can find what should be the setting of the outlet. So that is how we utilize it. That is what the concept of flexibility is, and how we utilize it in actual design of the channel. So if we go towards that derivation, that if flexibility is the ratio of these two rate of change of discharges, how it is equal to m over n d over h. So stating that discharge in the parent channel is a function of the depth power n, k times d power n, k1 times d power n, then rate of change, then differential of that discharge can be written as k1 times n times d power n minus 1 into differential of depth. So that is the differential of the right hand side, k1 times n times d power n minus 1 into dd. ठीक है, यहाँ तक ये डिफरेंशियल फाइंड किया है लेफ्ट हैंड साइड का और राइट हैंड साइड का. So this differential d power n minus 1 can be written as d power n divided by d. So in next step, they have just replaced d n minus 1, d power n minus 1 by dn divided by d. And then they have combined these things, n, if you see this k1 into dn, so that is nothing but this discharge itself. So in this equation, they have replaced k1 into d power n with q. So they have written as n into q into dd over d. And now taking this q on the left hand side, we can write that rate of change of discharge in the parent channel to the discharge in the parent channel can be written as n times. And keep in mind this n is the exponent of the discharge equation for parent channel. So rate of change of discharge per unit discharge of the parent channel is actually n times rate of change of depth to the depth of the parent channel. So this we have derived from here by taking the differential. Similarly, if we write the equation for discharge in the outlet, we can come to the similar output. Take the differential, replace the m times h power m with the small q, bring this small q on the left hand side. Similar expression we can write, but with other symbols for outlet. dq over q is equal to exponent of the discharge equation in outlet, m times dh over h, that is the rate of change of head in the outlet. So when these things are known, in the numerator it is d small q, in the denominator it is d capital Q. So replacing these two things in the definition, equation of the definition of the flexibility. So replacing over here these two known values, so we can write this flexibility is equal to m into d divided by n into h into dh over d. Got it? ये चीज़ें हमने रिप्लेस कर दी फ्लेक्सिबिलिटी की इक्वेशन में. Now you concentrate on this term dh over dd. This is saying change of head in the outlet and divided by change of depth in the channel. Now see the cross section again. So if there is a small variation of the head or depth in the distributary, so same will be dh, same will be dd. If there is a variation of the water level in the distributary, so it will cause a change of depth in the channel, by that we will be representing as dd, and same will be dh. So what if there is a fluctuation in the water level in the parent channel, that will cause same variation of the depth in the parent channel, that will cause same variation of the head in the outlet. So we can say that in case of outlet, dh and dd essentially are always same. So that is why we replace dh over dd by ratio by 1, because they are actually equal to each other. So flexibility can be written as equal to m over n into d over h, or m over n divided by h over d. So that is what we have written in our original equation, that flexibility can be said to be equal to m over n into d over h. So any query or question इसमें, इसको खुद solve करें. It is easy. We started with the general equation of the discharge. This is, we say this is very general equation of discharge. If we write it in detail form, it will be nothing but either Chazy equation or Manning's equation. When we say that let us make it a generic equation, a very general equation, we can keep all those values which are constant in a factor k1, and those values which can vary for outlet, for a distributary, that is the depth. So that we keep as a variable with the exponent n over here. Then taking its differential, we can find this. Similar behavior, similar treatment we do with the discharge in the outlet. तो ये करके ये हम derive कर सकते हैं. इसमें है किसी को questions, कोई मसला?
डेरिवेटिव किस वेरिएबल के लिहाज से ले रहे हैं हम सर?
हम लेफ्ट साइड का डेरिवेटिव नहीं, मैंने डिफरेंशियल बोला है. सो differential of dq will be equal to k times differential of d power n. So when we say differential of d power n, so that will be n into d power n minus 1 into differential of d. ठीक हो गया?
m और m की बराबर नहीं होगी सर?
n is constant for a certain distributory. This because distributory is not changing. So exponent n for one distributory will remain constant. N will vary if the shape of the distributory vary. If previously it was rectangular, now it is trapezoid, then n varies. Otherwise, n will be constant. K contains Manning's roughness coefficient, that will remain constant. K contains slope for a certain distributory, it will remain constant. ठीक है? So K will be considered constant, N will be considered constant, only depth and discharge are variable in this case. Okay. Similarly over here, these coefficient K2 will remain constant, M will remain constant for a certain outlet. Its value will change if outlet is changed. If previously it was open flume, now it is orifice, previously it was someone else, so then M will vary. But for one outlet, it will remain constant. ठीक है? Okay. Similarly, there is another terminology, we call it as a sensitivity of outlet. A little bit different, but similar concept. It represents the capacity or behavior and outlet with respect to its change of discharge by changing the depth of the water in the parent channel. Previously, we have seen the behavior of the outlet of changing of discharge with respect to change of discharge in the parent channel. But if we want to quantify the change of the discharge in the outlet with the change of the water level in the distributory, then we use the parameter, we call it sensitivity of the outlet. So it is a ratio of the rate of change of discharge of an outlet, that is dq over q. Now you know small q we are using for the discharge in the outlet. Capital Q we will be using for discharge in the parent channel. And now you know D is the depth in the water level, water depth in the parent channel. Over here they are using the symbol G. G is the gauge reading of the gauge, which is so set that G is equal to 0. So that we can see from the G kya hai? Actually G is same as H over here. If we have a gauge over here, if we place a gauge, staff gauge, if we place a staff gauge over here, which reads 0 when water level is at the crest level. So it means gauge 0 is at the crest level, and it reads a certain value as the depth increases in the channel. So it means that G is same as H over here, only the symbol they are varying. But so because this G is used in Iqbal Ali book also, so that's why we are using this symbol also over here. So sensitivity is the ratio of rate of change of discharge in the outlet with respect to the rate of change of depth or gauge in the parent channel. dG over G, variation of the gauge, which is showing the head above the crest, variation of the gauge, which is showing the variation of the head above the crest per unit depth of the parent channel. So this S is sensitivity. This is called sensitivity, and it can be defined as the ratio of the rate of change of discharge of an outlet to the rate of change of depth of the flow in the parent channel. The similar thing is expressed. Previously we used the word gauge over here. Here we are saying the depth in the parent channel. So we can prove that sensitivity and flexibility are related with each other by exponent n. Sensitivity can be proved to be equal to n times f. Keep in mind this n is not Manning's reference coefficient. This is exponent of the discharge equation in parent channel. N is exponent of the discharge equation in parent channel. So which is 5 by 3 for trapezoidal channels, and which have the side slope equal to half to 1. So इस तरह जो trapezoidal channel है उसमें 5 by 3 n की value 5 by 3 होती है. So its proof is there over here. Proof is simple. We know the definition of this sensitivity, dq over q divided by rate of change of gauge with respect to the depth of the channel. So this change of the gauge is same as the change of the depth in the channel. As we have previously told you, whatever is the dd, same is dh. So whatever is the dd, same is dg. So we can say that this change of the gauge is actually the change of the depth. So we can write this equation in this form also. Also, we already know the definition of the flexibility. It is the rate of change of discharges in outlet and the parent channel. And we have already proved that this rate of change of discharge in the parent channel with respect to original discharge can be written as n times dd over d. This thing we have proved in the 2 slides back. So this thing we will be replacing in this flexibility equation. In this flexibility equation, replace dq over q with n dd over d. So when we replace f in flexibility equation, dq over q n dd over d. So now you see what is this? Everything except for n. So this is actually the definition of sensitivity. This dq over q divided by dt over d, that is the sensitivity, rate of change of discharge in the outlet to the rate of change of the depth in the parent channel. So we replace this term in the flexibility equation with sensitivity. So we can say that flexibility is sensitivity divided by n, or otherwise we can say sensitivity is equal to n times f. So that is how they are related. So if you know flexibility and you know the shape of the parent channel and its exponent n value, sensitivity can be calculated. If some outlet has a flexibility of 1 and n value is 5 by 3, so its sensitivity will be 5 by 3. So it means 5 by 3 is actually 1.667, 5 by 3, 1.667. So if sensitivity is 1.667, what does it mean? By 10% variation of the depth in the parent channel, discharge will vary 16.6% in the outlet. So sensitivity is telling me sensitivity comes out to be 1.66 or 16.66%. 1.66 means higher than 1. So it will vary more. Discharge will vary more as compared to the variation of the depth in the parent channel. So that is how sensitivity is defined. That is how it can be computed if we know the shape of the channel, if we know the shape of the outlet. So other definitions which we should be knowing is and utilized in design of the or representing a certain outlet. Efficiency is the ratio of the head recovered in the outlet, to the input head of the water flowing through the outlet. There is a certain head on the upstream side. There is a certain head on the downstream side. So downstream side head is the head recovered, head available to the water course. So the ratio of the head on the downstream side to the head on the upstream side is called as the efficiency. Those outlet which causes more losses within the outlet, their efficiency is low. Those outlets which are very smooth and cause less head loss, their efficiency is considered higher. So efficiency represents the recovery of the head after flow pass through the outlet. So it is the ratio of the head recovered on the downstream side, or we call it residual head, downstream of the outlet to the head on the upstream side. So that shows how efficient an outlet is. If it is close to 100%, we say it is efficient. Uh, and if it is less than that, so it means it is losing a lot of energy. What does it means losing lot of energy? Losing lot of energy means it will not be able to command much area. If head recovered is not much, head recovered is less, so less area will be commanded. By commanding mean it will reach to the less area. Higher area will not be able to be commanded with that outlet. So a good outlet is that whose efficiency is high, and efficiency is calculated by the ratio of the head on the downstream side and the upstream side. There is a modular range or modular limits, and there is a minimum.
चैनल्स में सर मॉड्यूलर चैनल्स में हम एफिशिएंसी खुद से हाइड्रोलिक जंप प्रोड्यूस करके कम नहीं कर रहे होते.
हाँ जी, तो एफिशिएंसी ऑफ डिफरेंट काइंड ऑफ आउटलेट इज डिफरेंट, कांस्टेंट नहीं है. जहाँ पे हाइड्रोलिक जंप प्रोड्यूस हुआ है, वी आर गेटिंग सम अदर बेनिफिट आउट ऑफ दैट. हम चाह रहे हैं कि उसका डाउनस्ट्रीम का इफेक्ट खत्म हो जाए. ठीक है
जी बेहतर
So,
सर.
efficiency efficiency of the pipe outlet will be better, जिसमें hydraulic jump create नहीं हो रहा. Or of course efficiency of rigid outlet like Gibbs outlet will be not as good as case of pipe outlet. So from here we will be getting another information that pipe outlet can work while losing very less energy, less head, and if there is less head difference available across the outlet, then pipe outlet is the one of the solution. In pipe outlet, the mainly energy loss is because of the friction in the pipe. So if pipe length is limited, so that can also be reduced. There is no hydraulic jump created. It can be further reduced by making a bell-shaped inlet at the upstream side of the pipe. उसको हम क्या कहते हैं? Bell mouth pipe. Okay. Another concept is minimum modular head. So it is a minimum difference of the water level between parent channel and the water course. In the longitudinal section of the water course's outlet, you have seen head on the downstream side, you have seen head on the upstream side, or water level on the upstream side, or water level on the downstream side. So the minimum difference between the upstream head and the downstream head, which will allow the intended working of that outlet. It will continue to work as intended for higher head difference. Okay, higher head पे easily काम करेगा. But the minimum difference on which the outlet continues to work as a semi-module, so that minimum head difference is called the minimum modular head. It is a necessary minimum difference of the water level between parent and the water course to enable module or semi-module to work as per its design purpose. If it is a module, if it is a rigid, it should continue to work as a rigid. So that minimum head at which it continue to work as a rigid outlet, so that will be called as a minimum modular head. And if it is a semi-modular outlet, so that minimum head at which it will continue to work as a semi-modular outlet. So below that head difference, maybe it will not be working as per intention. Maybe it is working, but not as a semi-modular. Maybe it is working, but not as a modular outlet. So the minimum head difference at which it continues to work as per its intended design, so that is called as a minimum modular head. It should be, and this minimum modular head depends upon type of the outlet. For example, in case of open flame outlet, experiment have told us that the minimum modular head should be, minimum modular head is 10 to 20% of the gauge or head above the crest. G is the head above the crest. So 10 to 20% अगर head available है across the outlet, then open flame outlet will continue to work as per its intended purpose. Similarly, in case of adjustable orifice semi-module, So this is orifice module, and it's we have a block in it, and that block can be adjusted up and down. So we call it adjustable orifice semi module. So you should know these terminology, and very new terminology. So maybe 2-3 times you have to go through it, then you will be familiar with it. In case of open flume, 10 to 20% of the G is the minimum modular head. So we have to ensure that that where we are putting that open flume outlet, at least this much head difference is available. If that much difference is not available, so then open flume outlet will not be working as per its intended purpose. And in case of adjustable orifice module, it is 80% of HS and BT. HS is the head above the block, head causing the flow in the orifice semi-module, and BT is the width of the throat of that outlet. So that is 0.82 HS minus 0.5 BT. Similar for other outlets, from the experiences in the literature, they have told that what is the minimum modular head for this kind of outlet, what is the minimum modular head for this kind of. So modular head or minimum modular head is the minimum head difference across the outlet that will still make the outlet work as per its intended purpose. So minimum head, which will which will make the outlet working as per its intended purpose. So modular limits are those extreme values of the head differences, minimum and maximum. So modular limits are the extreme values of the parameter at which a module or semi-module ceases to be capable of acting as such. So there is a minimum modular head, there is a maximum modular head. After that, it will not continue to work as per its intended purpose. So these are the limits. So lower limit and upper limit. The range is the modular range is the range of the condition in which the module will continue to work as per its intended purpose. So these are some definitions we should be knowing. Coefficient of discharge is in the discharge equation. There is a certain coefficient which is the ratio of the theoretical discharge to the actual discharge, or actual discharge to the theoretical discharge. We want that for a certain outlet, it should remain as far as possible constant. In order to use the outlet as a measuring device, the coefficient of discharge should remain constant in the full modular range. Sometimes these outlets are used as a measuring device also, as a discharge measuring device also, because we have their equation of discharge. For example, we have the equation Q is equal to coefficient of discharge times width of the outlet times depth power 3/2 or depth power half. We have the equation. So if we only measure the depth above the crest, we can calculate the discharge. So coefficient of discharge, if we use an outlet as a measurement device also, so such an outlet is sometimes called as a metered outlet. Similarly, if there is a fall which is used to measure the discharge, we call that fall as a metered fall. So if we use a structure for measurement of the discharge also, we say that is a metered structure. So in that case, if we are using it as a metered structure, then its coefficient of discharge should remain fixed for a usable range of that outlet. There is a silt drawing capacity is we have to specify for a certain outlet, and it is said that it should take its fair share of the silt, and the fair share of the silt is considered as 110 to 115% of its discharge capacity. Therefore, the silt conducting power of the outlet should be 110 to 115% as compared to 100% of the distributory. So why 10 to 15% higher silt should be taken as compared to the silt concentration in the distributory? Because of some losses in the distributory, the conveyance losses in the distributory make water, loss of the water, but sediment remains inside the distributory. So we want that all the sediment should go through the outlet to the fields. It should not remain within the parent channel. That is hazardous for parent channel, that can choke that thing. So it is recommended that outlet should take 10 to 15% higher sediment discharges as compared to their discharge share. Silt drying capacity enhances. How can we control the silt drying capacity? Silt drying capacity depends upon the crest level. You are familiar, hopefully, that the sediment concentration is not constant with respect to depth in the channel. With respect to depth in the channel, top layer of the channel have less sediment concentration, bottom layer of the channel have higher sediment concentration. So if you see the sediment concentration curve with respect to depth, it increases as we go down. So we can increase the silt drying capacity of an outlet by lowering the crest, and we can reduce the silt drying capacity by increasing the crest. So when we fix the crest level, we also see what is the silt drying capacity, what is the suitable silt drying capacity for a certain outlet. Usually close to 90% or close to the bed, it takes 110% of its silt drying capacity. It takes 10 to 15% higher discharges of the silt. It should be easily adjustment if we want to carry out. So that's the characteristics of an outlet. So it should be easily adjustable, and it should be immune from tempering. It should not be easily tempered, because people try to change its shape to get more discharges. So it should not be. So structure should be such that it should not be easily tempered. So sometimes we place the steel plates at the bed of the outlet and steel plates on the side of the outlet, so that wear and tear should be less, one thing, and farmer should not be easily able to change it. And sometimes we put this steel plate with the bullets, with the nut bolts, and fix them over there. And if we want to adjust it, then we adjust those steel plates over there. So I stop it over for 5 minutes, and then we go towards the next topic, how to select a certain type of outlet in various conditions. And in the later part, we will be going through design of an open flume outlet, different steps in design of an open flume outlet. So after 5 minutes, I will join you back. Okay, welcome back after the break. There are 48 students left. Prior to break, there were 55. Okay. Hopefully, rest will be joining soon. So what we have gone through up till now, we have gone through different definitions which categorize, which represent the characteristics of the outlets, which represent different behavior of the outlet. For example, flexibility, sensitivity, minimum modular range, minimum modular head, efficiency, so things like that. And we are familiar with kinds of outlet also, semi-modular, modular, and non-modular outlets and their types also. We know their flexibility, we know their sensitivity also. Sensitivity represents the variation of the discharge in the outlet with respect to variation of the depth in the channel, while flexibility represents variation of the discharge in the outlet with variation of the discharge in the parent channel. So small differences, and these small things are usually asked in the Viva Voce examination in Public Service Commission. So you should be familiar with them because this is the final semester subject. So they expect that you will be more familiar with the final semester subject as compared to the first year subject. So they will like to ask such things like this, especially in case of interview of irrigation department. They will be putting more focus on irrigation subject. So selection of the type of the outlet, if we go towards this. This is mentioned in case of in book of Iqbal Ali also. So you can see Iqbal Ali, and this is taken from there, page 330 to 331 in the version in the what we call it in the Iqbal Ali edition. I have, I think, the third edition is with me. Maybe you have the later edition with you. So the edition which is available with me, in that it is page 330 to 331. The soft copy which is available to me, and I think I have shared it with you. And also the selection of the type of the outlet has been described by a research paper which was presented in Engineering Congress. Like we have the Pakistan Engineering Council, for which your registration is a must if you want to practice engineering in Pakistan. So Pakistan Engineering Council registration is must for you people for practicing engineering in Pakistan. Similarly, we have another organization whose registration is not compulsory, but their service to the engineering community is a lot. They have served the community for a long time. That is called as Engineering Congress. Presently, we call it as a Pakistan Engineering Congress. It is a group of engineers formed by themselves, and they are working together to disseminate the knowledge of engineering. And you can also become after graduation member of this engineering congress. So prior to Pakistan independence, this used to be called as Indian Engineering Congress. And when irrigation was being developed in this area, much research was disseminated through meetings of this engineering congress. So they have an active website available at the moment, and they are putting all the historical research papers over there. One of the main and extensive collection of the knowledge on outlets is given by this research paper number 264, presented in 40s by Mehboob and Gulhati. So these were the engineers of that time, and this paper extends hundred of pages. So I have downloaded it, and there are 3 PDF files available. So you can also download by going to the Pakistan Engineering Congress website and searching with respect to the outlet. You can go to this paper. So they have also mentioned how to select a type of the outlet. So their so there was a breakage in the net. Hopefully my voice is now coming again to you people. So let us continue again. Hopefully we are recording, and I have shared my screen also. So this Iqbal Ali chapter is written from, I think, this Gulhati paper, and this extensive collection of the history of the outlet, how they are developed, all the outlets which were being utilized at that time. So those are mentioned over here, and much in the Iqbal Ali book with respect to outlet is taken from this research paper. You should have this one. So if we want to select the type of the outlet, so these recommendations will help you selecting the type of the outlet. For example, it is said that if the channel or the distributory on which you want to install the outlets, it has a constant discharge and the water levels are not changing, then selection of the outlet type is not a big problem. You can select either rigid outlet or modular outlet or flexible or semi-modular outlet. Either of these you select, it will be getting the same discharge because there is not much variation of the depth or the discharge in the parent channel. Control the discharge by varying the water level in the downstream side. If you are getting my voice continuously, क्योंकि यहाँ पे मैसेज आ जाता है, please hold a minute, net is not good. I can change the net also if you have problem. आपको आवाज मेरी सही आ रही है? Anybody?
सर
Yes, yes.
डिस्टोर्ट होते हैं,
Distort
आती है फिर
होती
रुक जाती है.
है. Okay, मैं अपना net change कर रहा हूँ. I go to PTCL and I remove the UI. Okay, I have connected with a different net, BTCL net. I am using it hopefully without disturbance. We will continue it. So, first message to you people: if the distributor is expected to run on a constant discharge on without changing its water level much, either you select modular rigid outlet or semi-modular outlet. Same are the result. No big problem. But if it is not working, so we are not very lucky that all the distributors are working at the constant discharges and the constant water level. Reason is we don't get most of the time in the rivers water is not available as per the design discharge of the channel. So many times the water diverted to the channels, to the main channel, is less than the capacity of all the channels to whom this main channel is feeding. If there are 10, 20 distributed channels to whom a main channel is feeding, if we combine the discharge of all of them, main channel is not having that much discharge. So there are 2-3 different ways.
सर आप तो कह रहे थे कि हमारे पास मतलब ज़्यादा डिस्चार्ज होता है या नहीं है, ऑलमोस्ट 148 मिलियन एकड़ से, तो हमारे पास कैपेसिटी नहीं होती, तो हम जो 30 to 40 जो है वो हमारे पास यूटिलाइज नहीं होता.
That is on annual basis. 148 million acre feet is annual average flow. ठीक है?
ओके सर.
We have abundance of water in Kharif. We have so much water we cannot hold it. Flood आते हैं. But we have problem in Rabi. आजकल का जो सीजन है या इससे पहला जो गुजरा है, that is Rabi. अप्रैल से पहले जो सीजन था, that was Rabi. So problem comes in Rabi. Usually rivers are dry. सो मैं एक महीने में आपको 100 रुपये दे दूं और दूसरे महीने में मैं आपको 2 रुपये दूं तो एवरेज आपकी हो गई 51 रुपीज़. सो एक्चुअल दैट इज़ नॉट रिप्रेजेंटिंग द एक्चुअल केस. 2 रुपये वाले मंथ में यू विल बी शॉर्ट ऑफ वाटर, short of money. That is the case. So mostly in Rabi season, we don't have sufficient water, especially when these dams were not there. When these dams and reservoirs were not there in that time, we had to work on the natural supplies. The river used to be dry. ठीक हो गया, बात clear हो गई. So don't consider average
Yes,
water
sir.
is evenly available every month. That is not the case. Okay. So we are not so lucky that we are getting the required quantity of water. So one way of running the system is main and branch canal are working and keep the distributaries in rotation. Depending upon how much water is available, one distributor is run and then another distributor is run. One distributor is stopped, other distributor is given full supply. So if that is the case, so that is also showing that whenever water is available, that is at the full discharge. If they do this way of working, then it has been seen that in Rabi season especially, some these what the closure period, they call it closure period, is sometimes so much extended that the crops are affected. So at some places they are working, so that way of working, stop one distributary and feed the other distributary based upon the available water. That is good with respect to design of the canal, with respect to sedimentation in the canal, that is good. But in certain area, the closure period is so much extended, the crop gets affected. So some engineers, some operators, they then practice that, okay, let us run all the distributaries maybe at the lower discharges. So if that is the case, when discharge is not at the full supply, or water depth in the channel is not full supply, then there are certain recommendations which we can use to decide the outlet. So when discharge at the levels are likely to change, so if this variation is a temporary change of discharge, not for the whole season, then it is said that a proportional semi-module is desirable. Proportional semi-module. So they are recommended semi-module. One thing is that this rigid is usually recommended on the branch and main channel. So that is kept out. Branch and main channel, usually we don't provide outlets. If due to certain compulsion, कोई बहुत बड़ा landlord आ गया, मुझे यहीं पे चाहिए outlet, so then a fixed outlet can be given over there. Most of the time we are using the semi-modular. Or that non-modular outlet, that also is usually not recommended except when modular head is very less. अगर वहाँ पे head difference ही बहुत कम है तो फिर ये semi modular outlet don't work over there. So in that case we go to the non-modular. So now question is which kind of semi modular should be used? So semi modular में से proportional semi modular. And if I remind you, what do we mean by proportional? Proportional semi module is that one which has the flexibility equal to 1. It means whatever is the variation in the parent channel, same will be the variation of the discharge in the outlet. So it is recommended if there is a temporary variation of the discharge, go for the proportional semi-module, so that that variation, if it is increase of the discharge in the parent channel, that should go to the outlet. If it is reduction, that should go to the outlet. But if the variation is not temporary, it is seasonal variation for the whole season, and that seasonal variation is in the slope. Because of the variation of the discharges, if sometimes a channel is not working at the full capacity, there are chances that sedimentation will occur in certain part and the slope of the channel will vary. So when again same design discharge come, that slope is again come back to the design slope again. So seasonal variation of the discharge sometimes cause seasonal variation of the slope of the bed of the channel. So if that is the case, then it is recommended that go for subproportional in the lower reaches, and low flexibility means subproportional. So go for the subproportional outlets in which the variation in the discharge of the outlets should be less as compared to the variation in the parent channel. So if slope varies seasonally in the parent channel, then subproportional outlet is recommended. So in case of the channels which are running at the full discharge or full supply for a certain period and remaining closed for certain other period, इनको हम कहते हैं rotational channels हैं. So it is desirable to have hyper proportional or high flexibility outlets in head reaches. Remaining में जो है ना flexible ही देने हैं. Head reaches के जो चंद outlets होंगे, so those should be hyper proportional, so that initially when there is variation of the full supply, if there is a variation for a certain period, if it is working on the full supply for a certain period and remain closed for a certain period, so it should be hyper proportional. Hyper proportional means flexibility more than one, means it will be getting more effect. Change of discharge in the outlet will be more as compared to the change of discharge in the parent channel. So this is a silt drying capacity. I leave it, that is a separate thing. The last message in selection of the outlet is that for cases other than the above, so the 3-4 special cases are shown over there. For all the remaining cases, semi-module outlet are recommended. And out of the semi-modular outlet, it is recommended that orifice semi-module is recommended in upper and middle reaches, and adjustable proportional module is recommended in the lower reaches. These are the two kinds of the semi-modular outlets. So this one is recommended in the upper and middle reaches. So most of the time we will be having semi-modular outlet. Only variation will be whether they are hyper-proportional or sub-proportional. So most of the time we will be recommended proportional outlet, and except in case of variation of the discharge in the parent channel, somewhere we will be proposing hyper-proportional and somewhere we will be recommending sub-proportional outlets. Non-modular outlet are not recommended except when the modular head required for the semi-modular outlet is not available. If head available is very less, then non-modular outlet can be used. Rigid will be used in case of branch and direct outlet in case of the branch. In that case, we will be using the rigid outlets. So this is a guideline which will help you selection of the outlet. So mostly we use semi-modular outlet, and out of those orifice semi-module is used in upper and middle, and proportional adjustable proportional module is used in the lower reaches. So similar is the message given over here, that non-modular outlet should be avoided. So if you read this thing, so similar message which I have told you, non-modular should be avoided except when the working head is not available. Semi-modular is the device recommended most of the time, except whether it should be proportional or sub-proportional, that is mentioned over here. So now we go to the design part of an open flume outlet. Hopefully you know the differentiation between open flume outlet and between the orifice outlet. These both are the semi-modular outlet. In open flume, we don't have, we let the water flow through open channel. Its top surface of the water is open to the atmosphere, and the condition is not like a pressurized flow. So in case of open flume outlet, a weir with a throat is provided, and that work as a control section within a parallel throat for all the discharge up to the maximum. A hydraulic jump is created. A hydraulic jump is formed because of that weir and because of that throat. So a hydraulic jump is created that works as a control section, and the water level of the water course does not affect the discharge through this type of outlet. This type of structure is built in masonry. Usually brickwork is utilized to make it. This structure.
चेंज नहीं हो रही आपकी.
स्लाइड चेंज नहीं हो रही, ओके कब से चेंज नहीं हो रही? आई शेयर इट अगेन। होपफुली अब चेंज होगी, वो नेट चेंज किया था, लगता है वो स्टक हो गया था। इट्स वेरिंग नाउ, चेंजिंग। इससे पहले हमने आपको ये स्लाइडें दिखाई हैं, सिलेक्शन ऑफ द टाइप ऑफ द आउटलेट, and now I am on the slide 27, that is the design concept of the open flame outlet. So it is constructed in masonry. Usually it has a weir or raised bed and a throat or constricted width of the channel, and the top surface of the water in the outlet will be open to atmosphere. So that's why we call it as the flume outlet, open flume outlet. So its shape, its drawing will look like this. You should understand this drawing completely. You should know that over here we are showing in the plan view a distributor is shown over here. Width of the distributor is shown over here. On one side of the bank of the distributor is shown over here in the plan view. That is the top of the bank. This is the berm part of the bank. So in cross section you see this is the distributor itself, water level, a little bit raised berm. Then we have the bank, main bank, and because we have to link the distributor with the water course over here. Water course in the plan view is over here. We have to link it, so it is linked with through the outlet. So in open flume outlet, there is nothing but a channel provided with the constricted width. A channel is provided with walls on the both side. One side wall is smooth curved wall, the other side wall, the downstream wall, is simply a straight wall constructed in masonry. When it has to pass under the bank, then a slab is placed over here. तो यहाँ पे एक slab placed कर दी जाती है at a sufficient higher elevation so that it should not make this water make this channel as an orifice channel. So this slab should be kept to a sufficient higher elevation so that the open channel flow condition should maintain. So if open channel flow condition is maintained, then we can call it as an open flume outlet. तो यहाँ पे चूँकि ड्राइवेबल बैंक्स होते हैं, banks are drivable, so we have to put a slab at the top, and then the earthwork of the bank is done over there. So downstream side, it is attached to the water course, and usually the water level in the water course does not affect the discharge because of this creation of the hydraulic jump within the outlet. So while we are designing it, main thing to design is how much should be the width of this throat, BT, width of the throat we need to decide. Elevation of this crest need to be decided. And rest things are more or less standard, and we can take the guidance from this drawing. How much should be the radius of this curvature, 2 times h. How much should be the radius of this wall, 2 times h over here is also the radius of this wall. How much should be the length of the throat? So this length of the throat should be how much? 2 times h. So how much should be this length, and how much should be the expansion of this width after throat is finished? How much should be the slope of the expansion over here, 1 in 10 to 1 in 15? So these parameters are more or less fixed for open flume outlet. The things which we have to decide is the width of the throat, and of course the width of the throat will be dependent upon how much discharge we want to pass through this outlet, how much and how much is the head available which causes that discharge. So these two things control the width of the outlet. And the crest level I have already explained to you, that depends upon whether we need proportional outlet, hyperproportional or subproportional. So that depends upon the flexibility we have selected. That will tell you how much should be the H over D ratio. That will decide the crest elevation. So that is a summary of this thing. Usually masonry work, 1 inch, 9 inch wall is sufficient, considered to be sufficient, except for some part where 2 brick wall is required. For example, this 58 centimeters. So this drawing is made in centimeters. Our dimensions are in centimeters. So over here, only this part is 2 brick thick wall. The rest of the walls are 9-inch wall over here. Bottom is protected with the help of concrete layer with the lining of the bricks on their edges. Here is the lining of the brick on the edges. So that is a protection against the scouring or against the damages in the long run. So we, as a hydraulics part, we have to decide the top of the crest, we have to decide the width of the throat, and we have to take the standard recommended radiuses and the length from this drawing, and we can decide or design the open flume outlet. So same thing, I have put it in a larger size for your guideline. Different radiuses. For example, radius of this vent is given as 2 times h. The length of the throat is also given as 2 times h over here from the start to the throat, and then from the throat to the next part also, that is also 2 times h. Over here about 1.5 meter expansion is given. That depends upon bank width. जितने बैंक की width है ये उस पर depend करेगा. So that varies with the canal to canal. So let us, similar thing is shown over here also. If D is set to be the depth of the water in the parent channel, H is the head. So then this crest should be from the start of the outlet, it should be 2 times H away from. So this transition should be within this. The radius of this transition is 2H. Again, a 2H distance is provided in which the width is constant. Throat width is provided in this part, and then a expansion is given. So we expect that this hydraulic jump will be created within this length. Hydraulic jump will be created within this length. So 2H is considered sufficient for that purpose. How much thick is the bed? They are telling 150 centimeter, 15 centimeter, 150 millimeter, about 6-inch thick concrete slab. Whenever we have to finish the concrete or the lining, we have to protect it with the help of the edge wall, or they call it इसको क्या कहते हैं, a toe wall. So a toe wall need to be created to not much depth over there. So slab is provided at the top to support this bank. If it is not drivable, you will see a channel over here. If we don't put this slab over here, you can see simply a channel over here. So, but to make it drivable and to passable, they place a slab over here. Because the span is not much, so slab design is not a big problem over here for you people. 75 millimeter thick precast RCC slab is recommended because width is usually few inches. Width over here is few inches. If we have to design an outlet, we need coefficient and that discharge equation. For open flume outlet, we can use a Weir equation. That is a kind of Weir equation. Discharge is equal to coefficient times width of that flume, BT, width of the throat, into H power 3 by 2. For open flume outlet made in masonry, this coefficient varies in FPS system. This coefficient varies from 2.9 to 3, depending upon the width variation from 0.2 feet to 0.4 feet. That is the normal range for such kind of outlets. Usually the outlets have the size, discharge varies from 1 cusic, 2 cusic, upper limit 3 cusic or 4 cusic. These are the sizes of these outlets. How to select the size of the outlet? The recommendation given by that paper of Gulhati, they say that it should be the discharge in the outlet or discharge in the water course should be of such quantity that a farmer can handle it at a time. It should not be such a big channel that he cannot handle it. And usually, because the farmer are also practicing the tube wells or well irrigation also, so they have the channels made in the field for that purpose also. So similar amount of the capacity should be there for the water course which is taking water from the canal. So it is recommended that 2 cusic outlet is most of the time is considered suitable for work in the Punjab area. So 2 cusic outlet are considered as a recommended, but variation is there. 1 cusic outlet bhi hote hain or 3 cusic outlet bhi hote hain. So it should be depending upon the ease of the farmer, how much water he can handle, and it should not be so small capacity that it takes large time for irrigating a standard area, half-acre area. If he want to irrigate at one time, so it should not be taking much time for him. Usually they say that they make the field equal to the half-acre of the land. So that is the guideline for selection of the size of the outlet. So we usually go for the 2 cusic outlet, and if there is special need, we can go to 3 or 1 cusic outlet. So C value we will be selecting based upon the throat width. When we have to design an outlet, throat width is initially not known to us. H is usually we calculate from the setting of the outlet. H is known to us. So if we assume a C value out of these, assuming that our throat width will be in a certain range. For example, for 3-4 cusic outlet, if we think that it will be 2.5 to 3.5 inch of the throat width, C value can be selected as 2.9. So if we assume a certain BT range and select a C value, put that C value over here. H is from the setting of the outlet. Discharge is, we have selected that we will be making a design of an outlet of so much discharge. So BT can be calculated. If that BT is within that assumed range, that C value will be considered as final. Otherwise, we will go for another cycle, changing the C value, and we will be finding the BT value. So quite easily we can calculate BT value, throat width, which is required to pass a certain discharge. For example, you are designing a outlet of 2 cusic discharge, and setting you have done such that H is known to you, so BT can be calculated from here. Here is a solid example. Design an open flume outlet. Sometimes we call it as a crumbs outlet also. Outlet discharge required is 4 cusic. Depth, full supply depth available in the parent channel is 3.5 feet. Working head available. What is this? This is the water level in the parent channel and the water level in the water course. So their difference available is 1 feet. So the minimum modular head for the open flume channel, open flume outlet, we have been told in the previous slide, it is 0.1 of G to 0.2 of G. So that minimum modular head, whatever we calculate, that should not be beyond this available working head. So we have to check that one. So discharge in the distributory is 60 cusic. So we need an outlet of 4 cusic, parent channel, which is usually already designed over there, whose dimension are usually known to us. Parent channel has a bottom width of 38 feet. Our depth is 3.5, side slope is 1.5. So these things will be known to you for parent channel, or you can calculate these dimensions from uniform flow formula. Manning's equation से आप ये calculate कर सकते हैं. For a 60 cusic channel with a depth of 3.5 feet, you can decide these things, assuming a suitable N value for unlined channel, that is 0.0225 or close to that. So if these are the input known to you, so first thing is decide the setting. So usually we recommend that it should be a flexible proportional outlet. It should be a semi-modular proportional outlet with flexibility equal to 1. And we have previously seen that for open flume outlet, M and N are 5/3 and 3/2. That results that the flexibility is equal to 0.9 times D over H. Flexibility is 0.9 times D over H. From that information, if we keep flexibility is equal to 1, this G over D or H over D, gauge over depth of the water in the parent channel, or head in the outlet over depth in the parent channel. So that should be equal to 0.9 if we want flexibility equal to 1. So this information is coming from selection of the flexibility. So for one flexibility, G over D need to be put to 0.9. So G can be calculated as 0.9 D. So D is the depth of the water in the parent channel. Putting that value over here, we can find that the G should be 3.15. It means this is represented as G. So that should be 3.27 or whatever we have calculated for a D of 3.5 feet. For a D of 3.5 feet, G should be 3.15 feet. So crest level is decided in this way. Now come to the decision of BT. So assuming that we are having a throat width in the range of 2.5 inches to 2.5 inch to 3.5 inch. So we are assuming that C value is 2.9. So assuming a C value of 2.9, putting this G as 3.15, Q is 4 cubic, we can calculate BT. So BT will come out to be in feet, convert it into the inches, or see whether this is within that range of this CD. If that is within that range, so this BT is final, so 0.25. Usually we don't recommend an outlet whose width is smaller than 2 inches. Smaller than 2 inches. Reason is it's frequent choking of that outlet because of the trash coming to the area. So we should not go to a smaller outlet than 2 inches, 2.5 inches. The value. So it means our assumption of CD 2.9 was fine because BT calculated is 0.25 feet. So two main parameters have been calculated over here. The rest are the geometrical parameter which drawing will help us. Length of the crest should be 2.5 G, radius of the transition 2 times G, and G is already known. One thing is setting back. Setting back is how much is the upstream wall. It is the distance by which upstream wall parallel to the distributary axis is set back, how much it should be set back. If I show you in the drawing, then you can easily understand it. What is a setting back? Not over here, over here I think. So if this is the wall of the upstream side and this is the wall on the downstream side, so how much this wall is set back as compared to the downstream wall of the outlet. So how much it should set back, it should be, it is controlled by the ratio of the discharge of the outlet to the ratio of the discharge in the parent channel. Got it? So setting back of the wall of the outlet, the upstream wall is set back as compared to the downstream wall by a ratio which is same as a ratio of the discharges of the outlet to the parent channel. So that is what is explained to you over here. Setting back bears the same ratio as the ratio of the discharges of the outlet and the parent channel. So if we calculate the ratio of the discharges of the outlet Q over capital Q, so that comes out to be 4 divided by parent channel discharge is 60 cubic. 4 divided by 60 cubic. So that much should be the setting back. So 2.53 feet is selected as a setting back. The distance by which the upstream wall parallel to the distributary axis is to be set back bears the same ratio to the width of the distributary as the discharge of the outlet to that of the distributary. So this ratio we have calculated, that comes out to be 4 divided by 60, 1 over 15 ban jayega. 1 over 15 multiply by width of the distributary. Width of the distributary was 38 feet. Width of the distributary was 38 feet. So 38 feet divided by 15 will give you how much should be the upstream wall of the outlet set back as compared to the downstream wall. ये clear हो गया? How much should be the transition as given in the drawing? It should be 2 times G. Downstream transition 1:10 to 1:15. How much should be the length? Depends upon the length of the bend. Modular head, we have to check whether it is within the available head. So for orifice flume, for open flume outlets, required minimum modular head is 0.1 G to 0.2 G. If I take the higher value 0.2 G, so minimum modular head required is 0.63 feet. Available head is 1 feet. So if minimum modular head is equal to or less than the available working head, we say that it will work as per its intended purpose. Flexibility we can check, but because setting we have done in such a way that the flexibility we've prefixed to 1, so we can be sure that flexibility will be 1. Because we put this D over G based upon 1 flexibility in the initial part. So just rechecking this is done over here. Sensitivity is N times F. So its sensitivity is calculated as 5 over 3. How much is the efficiency? Is the downstream head divided by the upstream head. So head on the upstream side, that is the head put in, minus the working head, that is a 1 feet head available. So difference of these will be the head on the downstream side divided by the head on the upstream side. So 3.15 is the upstream head, the working head is 1 feet, so 2.5 is the remaining. 2.15 divided by 3.15 is 68% is the considered the head efficiency of this outlet. So these are the few things, and then later part is the making of the drawing. So this drawing will help you in making the drawing for actual construction of the outlet. We have decided mainly the crest, we have decided the width of the throat, we have decided the setting back of the outlet. The remaining dimensions, radius, these thicknesses, these throat length, so these can be taken from this drawing. Here is a toe wall, so this toe wall depth is 27 centimeter and the 15 centimeter pad at the bottom. So that is how we design a simple open flume outlet. Similar is the concept for design of the adjustable proportional module. In adjustable proportional module, we have a roof block available. So this roof block makes pressurized flow through this outlet. So that becomes an orifice module. So we call it as, and because this roof block is movable, if we want to change its capacity, so we say that this is adjustable orifice module. So for this discharge equation is not same as the Weir equation. Over here it will be CD times Y times BT into HS power half. So this equation is used. If we want to make it proportional, its G over D should be 0.6. For flexibility equal to 1, its G over D should be equal to 0.6 rather than 0.9 in case of the open flume. And these are the terminologies, are the symbols used. Crest elevation or the gauge is G. HS is a head up to the bottom of the roof block. Y is the opening. And again hydraulic jump is created inside it. Downstream water level from the upstream water level difference, this is the head loss, HM. This is the head difference between upstream and the downstream side. So CD into Y is the opening, BT is the width which is not visible over here, throat width, into HS power half. So this can be used for calculating the BT if HS and G are prefixed based upon flexibility. If flexibility is decided as 1, we can find how much should be the G for a certain depth of the distributary, and then we can divide this. Again, internet was making problem. Let me take the attendance, and please go through this. There is a solved example in Iqbal Ali. Please solve this adjustable proportional module yourself, and we conclude this lecture on the outlets over here. The last slide is the tail clusters, and tail cluster I have explained already. When the discharge in the channel is less than 5 or equal to 5 cubic, we don't put only one outlet. All the discharge is divided into a number of outlets. They can be 2, they can be 3, they can be more than 3, depending upon how much is the discharge at that place. So a group of the outlet is called as a tail cluster. This drawing help us design different kind of the tail clusters. So I stop it over here. Please go through the design of the adjustable proportional module, whose characteristics are mentioned over here. Its solved example is there in Iqbal Ali book also. BT and Y we need to propose, and then its drawing need to be made. So here is the adjustable block over here. ये वो block है जो इसके discharge को control करता है. So I stop over here, I take the attendance, and then say you Allah Hafiz. If you have any question, you can ask me now. Download attendance. 49 students are left. So attendance is taken. You are free to go if you want to. There is a slide over here. Total channel control. So in this video, in YouTube video, they are showing the modern way of distributing water with the help of the wireless remote control and computerized control. So go through this video, which is the future of water distribution in Pakistan or in elsewhere. Downloads. So I have put the attendance in sections. CR is requested to please keep a record of this attendance in Excel form. Combine them together. Okay, if no more questions, I stop the recording. Thank you very much. Who is it?
सर एक दो प्रॉब्लम्स हैं.
The 147.
सर हेड रिकवर एफिशिएंसी के साथ रिलेट है, तो हम सर इंटेंशनली हाइड्रोलिक जंप क्यों फिर प्रोड्यूस करवाते हैं?
Intentionally, इसका जवाब मैं दे चुका हूँ. We don't want a non-modular outlet. बात समझ आ गई? अगर मैं हाइड्रोलिक जंप
सर काइंडली रिवाइज कर.
if I don't provide hydraulic jump, it means downstream water will be affecting the discharge. So that is a non-modular outlet. Non-modular outlet we want to avoid, except in special cases when other outlets are not working. मैंने ये जवाब पहले दिया है. तो people recommend, experienced people recommend go for semi-modular outlet. So if you can create independence from the downstream water level by some other way, don't create hydraulic jump. लेकिन अभी तक जो एक्सपीरियंस लोग हैं उनके पास और तरीका नहीं है कि डाउनस्ट्रीम के इफेक्ट को कैसे खत्म करें, इफेक्ट ऑन द फ्लो इन द आउटलेट. So they know only this way, that if you create hydraulic jump, downstream water level have no effect on the discharge. ठीक है, बात समझ आई? So when we get one benefit, we are losing another thing. That's true. So usually we have sufficient head available that it works. Usually the head available is more than minimum modular head. तो 1 फुट अगर मौजूद है हेड डिफरेंस, तो हमारा काम चल जाता है.
सर मॉडुलर आउटलेट जो है वो दोनों तरफ के किसी भी लेवल पे डिपेंड नहीं करता, तो फिर हम किस तरह इसको डिजाइन कर सकते हैं प्रोपोर्शनल, हाइपर प्रोपोर्शनल या सब प्रोपोर्शनल के केस में, जबकि वो इफेक्ट हो रहा होता है लेस और मोर?
जो मॉड्यूलर आउटलेट है उसकी फ्लेक्सिबिलिटी 0 होती है. As we reduce the flexibility of a semi-modular, it goes towards modular outlet. जब वो 0 हो जाती है, when it does not affect, तो फिर हम उसको रिजिड कह देते हैं या मॉड्यूलर आउटलेट कह देते हैं.
सर अभी न्यूमेरिकल प्रॉब्लम में हमने सेमी मॉड्यूलर जो डिजाइन किया है उसमें हमने प्रोपोर्शनल रखा है।
सेमी मॉड्यूलर प्रोपोर्शनल, हाँ जी, फ्लेक्सिबिलिटी 1।
तो लेकिन सर आउटलेट पे जो डिस्चार्ज है या वाटर कोर्स का वो तो इफेक्ट उस पे तो डिपेंड नहीं करता।
दोबारा
सेमी
बोलो,
मॉड्यूलर बाय डेफिनेशन सर,
दोबारा बोलो।
बाय डेफिनेशन ऑफ सेमी मॉड्यूलर सर, जो लेवल ऑफ वाटर इन द वाटर कोर्स है वो इस पे डिपेंड नहीं करता कि कैनाल में कितना डिस्चार्ज है।
Level of the water in the water course don't affect the discharge in the outlet. That is semi-modular. Level of the water in the water course don't affect the discharge in the outlet.
तो लेकिन प्रोपोर्शनल की डेफिनेशन में तो सर दोनों तरफ इफेक्ट जा रहा है
ना
बराबर।
ना ना, प्रोपोर्शनल में कहाँ हमने कहा है कि डाउनस्ट्रीम वाटर, प्रोपोर्शनल इज फ्लेक्सिबिलिटी इक्वल टू 1. फ्लेक्सिबिलिटी इज rate of change of discharge of the outlet, not the depth of the water in the outlet, in the water course.
ओके सर।
F is equal to dq, d small q और q divided by d capital Q और q. कहीं हेड की बात नहीं आई उसमें।
जी ठीक सर, ठीक।
Okay, thank you very much.
थैंक यू सर।
I stopped the recording.